Hello, and thank you for joining us for our Tech Talk. My name is Eric Hopenians, and I will be discussing Indiana Microelectronics' Navy STTR Phase 2 program. Our Phase 2 program focuses on tunable filters for GPS and SATCOM resiliency under the STTR topic number N11A-T016. This topic is a NAVWAR-sponsored effort. Indiana Microelectronics was founded in 2009 to develop and commercialize tunable and reconfigurable microwave filters. Our company currently designs and manufactures real-time reconfigurable RF and microwave filters for co-site interference and jamming mitigation and for next-generation frequency-agile transceivers. We have developed and delivered filters covering UHF through the KU bands. Our company is a non-traditional small business located in West Lafayette, Indiana. We have experience in several SBIR and STTR programs with multiple branches of the DoD, including the Navy, DARPA, Air Force, Army, MDA, and NASA, with some of the SBIR and STTR efforts resulting in additional Phase 3 funding. Our team has also participated as subcontractors in the National Spectrum Consortium program and is currently the prime contractor on a DARPA WARP-sponsored effort. Our filters have been demonstrated in fielded systems and have reached TRL 7. We have an experienced technical and management team and are proven team players and contributors with various DoD primes and academic institutions. The Navy, as well as other branches of the DoD and many commercial applications, are experiencing adverse effects from an overcrowded radio spectrum and ever-increasing use of wireless systems. The electromagnetic spectrum is a limited natural resource, and with a demand for increased bandwidth and increased threats from adversarial sources, solutions that can enhance a system's resiliency against such threats are needed. In today's operational environment, Navy RF and microwave systems must operate through several threats, including large signals from friendly and adversarial jamming sources, wideband noise generated from nonlinear devices, and multiple wireless systems operating near or at the same frequency. The problem is further compounded in Navy applications where space is limited and physical separation between sensitive receivers and high-power transmitters is limited to a ship's available real estate. Tunable and reconfigurable microwave filters have been shown to be effective system components for the mitigation of harmful interference by suppressing the unwanted and harmful signals while selecting the desired signal or spectrum of interest. However, to maximize their effectiveness, any filter inserted into a system should exhibit low insertion loss and high out-of-band rejection. Two characteristics that maintain signal integrity while effectively suppressing undesired interference. And when covering a large spectrum of interest is required, wide tuning range is also a desirable filter characteristic. Filters based on yttrium iron garnet, or YIG, spheres have been available in the marketplace for decades now. The filters provide a wide tuning range to cover a large spectrum of interest, have a low insertion loss performance, and provide high out-of-band rejection. However, traditional YIG filters are physically large, and due to their tuning characteristics, they require large amounts of power to be consumed. Therefore, when size, weight, and power are key characteristics in a system's development, a traditional YIG filter falls short for meeting the metrics. Thin film YIG filters, however, can overcome swap disadvantages of their YIG sphere counterparts while preserving the desired filter characteristics. YIG film-based filters have been shown in literature to provide low insertion loss and high out-of-band rejection in a much smaller form factor. The smaller form factor requires less current to produce the magnetic field strength needed to tune the filter. Both attributes allow for a reduction in the size and power consumption of the filter. Given the potential impact on swap considerations when YIG thin films are leveraged, the Indiana Micro team, along with our subcontractors, the University of Dayton, and Winchester Technologies, have proposed to develop YIG thin film filters for interference mitigation in the GPS and SATCOM bands. Our team is currently depositing YIG thin films on GGG substrates using pulse laser deposition techniques, or PLD. To date, the team has deposited YIG thin films on GGG substrates with film thicknesses up to 400 nanometers. The films have been shown to produce low ferromagnetic resonance line widths, a desirable attribute for high-quality YIG films. The team is currently building upon this progress and refining our processing parameters to further decrease the line widths and increase the film thicknesses. By the end of the Phase 2 base efforts, we intend to produce films as thick as 3 microns while maintaining low ferromagnetic resonance line widths. Along with developing the PLD deposition techniques, the Indiana Micro team is designing and analyzing initial tunable filter prototypes based upon thin film YIG materials. Several designs are in progress that leverage both normal biased YIG films as well as in-plane biased films. Some of the initial designs have been completed, and prototype testing is anticipated in the first quarter of 2024. There are several key features, advantages, and benefits associated with the YIG film filters under development through this STTR Phase 2 effort. Features include high-quality YIG thin films that enable low filter insertion losses. The film-based filters result in both lower size and lower power consumption. Furthermore, multiple film resonators can be coupled together in a single filter design, increasing out-of-band rejection and enhancing the system's resiliency against strong interference. The filter concepts also provide multiple advantages over their YIG sphere counterparts. The advantages include a reduction in both size and power consumption, addressing swap concerns for current and future Navy RF and microwave systems. Furthermore, the high-performance, frequency-agile filters provide the selectivity and low insertion loss necessary for preserving signal integrity while rejecting the harmful interference that has been shown to impact the system's performance. The benefits provided by the features and advantages of YIG thin film filters include maintaining both signal integrity and link performance when operating in hostile and crowded radio spectrums. The enhancement of the system's resiliency in such environments will allow the Navy and other DoD components to preserve spectrum and interference dominance. There are multiple key markets beyond GPS and SATCOM applications. One of the fastest growing markets is 5G infrastructure. There's a growing use and deployment of 5G infrastructure, and interference issues with 5G deployment have already been realized, most notably in the aviation industry, experiencing 5G interference in C-band systems. Furthermore, 5G deployment has impacted C-band SATCOM communications. As the infrastructure continues to grow, so too will interference concerns. S, C, and Ku band radars could also benefit from the technology under development. As with other wireless systems, signal integrity is a major factor for radar operations. Highly compact filters that can integrate into next-generation phase array systems are sought, and thin-film YIG technology has the potential to meet radar filtering demands. Also, EW systems are impacted by highly contested and congested RF environments. Frequency-agile filters with the ability to tune over wide bandwidths are ideal candidates for such systems. The demonstrated ability for YIG filters to tune over an octave are ideal candidates for EW systems. Therefore, insertion into EW applications will be explored as the technology matures. Thank you very much for your time today. If you have any further questions or inquiries, please reach out to our Business Development Manager, Mike McFeeters.